Hi everyone. So today we're just going to finish up chapter 9 with the regression. So this is just going to be a continuation of what we'd already started last week. So just as a quick thing to help you go along, make sure you have the data sets. I believe for this we're going to be using record 1, and this will help us run our regressions in SPSS. So just a quick review, right? Remember, when we are looking at correlation and regression, we're interested in the association between two variables. And these two variables happen to be continuous variables. So we kind of add to our knowledge about the different types of tests we can do. And here we're doing two variables that happen to be continuous. So remember, there are a couple differences between a correlation and a regression, where with the correlation, what we're interested in is looking at an association between two variables, and it's basically measuring the correlation coefficient, which is the tightness of those points to some linear slope between the two lines. Where in chapter 9.3, what we talk about is linear regression, which is, again, an association between two variables, but we use those associations and talk about how strong that line is. So is it a strong effect or is it a weak effect, right? It's not about how close those points are. It's about where the points on a line tell you the effect of changing one changes the other variable. Okay, and in regression, we can use this, the equation that we generate to make predictions on what we've seen before. So I'll get into it and it'll make a little bit more sense when you actually see the data. So again, this is 9.3. So remember, simple linear regression is the association between two variables by finding the equation of a straight line that represents the relationship. So with simple linear regression, we have one predictor and one outcome. So the straight line that we create is the regression line. Right? The equation is the regression equation. Right? So if you think back to any algebra you've seen where you've done like the point-slope form or the slope-intercept form, that's basically what we're doing here. Is we have a point or multiple points, and we basically are trying to draw the best line that goes through our points, and we want to quantify like what's the slope of that line. That's what we're interested in, and that's what we call the regression model. So with regression, there are a couple of different approaches we have. So we can either do simple regression, which is only including one independent variable, or what we have is multiple regression, which is we can have more than one. So we won't cover this in this class, the multiple regression part. We only want to cover a simple regression, which is one independent variable and how it affects one dependent variable, right? So in all these cases, we only have one dependent variable, but we can either have one or more independent variables. Okay. Our linear regression describes this relationship, like I said, right, using an equation of a line. So the outcome of the interval, right, the outcome of this interest must be at the interval level. So it has to be continuous. Okay, like I mentioned before. So we've seen this before, right, in correlation, is where we're looking at the relationship between an x and a y, and we talk about it in terms of straight lines. So what changes in regression is that we have two things. So not just a line, we have what the slope of that line is. So it's the gradient, right? Is it moving at a very high rate, increasing up, or at a less high rate, right? Or is it decreasing very quickly, or is it decreasing not as quickly, okay? But what we also have is the point at which the line crosses the vertical axis, which we call the intercept, right? So like I've mentioned, you've seen this kind of stuff before, and this refers to what we call the slope-intercept form, right? So this is the equation for the linear regression, which you see in the highlighted box here. So it's called y equals beta naught plus beta 1 times x plus some error term, right? And I'll get to how that's related to what you've seen before on the next slide. So this is defined here, right? So yi is the outcome we want to predict, right? So say we want to predict your blood pressure given your lipid level, for instance, right? So maybe you have, you want to see how tall somebody is given their HDL levels, okay? So y would be the outcome that we're interested in, so the height of a person, okay? The parameters beta naught or beta naught here, the beta 0, and beta 1 are the regression coefficients. So sometimes we write them as the beta in capital Greek terms instead of just regular beta. So beta naught is what we call the intercept. This is the value of y when x equals 0. So it's the point at which the regression line crosses the y-axis. So this is called the intercept in our slope-intercept form. Okay, so if you draw kind of your cross in your x and y-axis, the y-intercept, or the intercept of that beta naught term, is where the line is going to cross when x is equal to 0. Okay, so so anywhere this crosses here on our y-axis, this is going to be the y-intercept. So it could be here, could be here, could be in the middle, right? It could be positive, it could be negative, it can be any value. As long as it's crossing the y-axis, it's our intercept. Okay, the beta regression coefficient for the predictor, or beta 1, which we see here, is the slope of the regression line. So that tells us about the direction and the strength of the relationship, right? So with correlation, all we had was really directionality. With regression, we also have the strength of the relationship. And what I mean by strength is, what is that slope? And like I kind of alluded to, where is it increasing at a very high rate? So that would be a very high slope, a high positive slope, or something that's less steep. So that's still positive, but less so, right? Or is it negative at a high rate, or less negatively sloped? And so the last term we have is this error term, what we've kind of seen before, and that's just telling us our error, right? So everything we have always revolves around us having some error, right? We can't measure everything perfectly. So what we call our E, or our residual term, is really, it's the difference between the line that we've created, right? The best fitting line that fits all the points equally, in kind of in between, right? So if you can imagine all the points really being like a scattered cloud, right? Where's that best fitting line that goes in between, right? It's right in the middle. So our residual is the distance, right, between each point to the line. So that's our error term, right? Because we aren't able to explain with our regression the error that's there. Okay, so that's why we call it an error, because it doesn't give us all the information we need when we do our regression line. Okay, so like I mentioned before, right, we both have an intercept and a slope, and I drew a really ugly picture, but this shows it a little bit better, right? So the left figure, these two lines both have the same intercepts, but different slopes, right? So they both cross around here at around 48 or something. The intercept is 48, but one has a positive slope, the red line, and one has a negative slope, the green line. In the right figure, they have the same slope but different intercepts. So see, they're increasing at the same rate in a positive direction, but they all start at some different point of the y-axis. Okay. So lastly, what we're doing is we want to fit the best line that fits our observed data between our x and our y, right? So how does HDL predict your height? Then you estimate the slope and the intercept of that line. And the best thing that you can do, given regression, is that you can predict the value of an outcome given that you have an equation already. And I'll get to how you can do that in a second. But that's one of the good things about regression, is that given that you know something, you can predict what something in between would look like, or something outside of the range that you have, right? So say you created a model and you wanted to predict somebody's height, and you knew that height and HDL were associated. You could plug in a value for HDL and get a value for height. And what would you expect given you thought that this line would hold? So make sure you go over these terms and you understand what these things mean. Okay? So what we do when we find the regression line, it's the line that best fits the observed data. So what I've kind of alluded to most of this class is we want to try to find the best fitting line that always fits through all the points as equally as possible, minimizing how much residual or how much error we have. So that's how this method works, which is called the method of least squares, right? We take the smallest variance between each point to some line that we do. So what happens in SPSS or in any kind of statistical software is just trying a ton of different lines and basically trying to minimize the distance from each point to the line, right? And it keeps refitting and redrawing each line and minimizing the sums of squares distance between the point to the line. So the line of the best fit is the line that results in the least amount of difference between the observed data, right? So our data that we've collected and the line predicted by the model. Okay, and when any line is fitted, obviously there's going to be a difference between those predicted values, right, just the straight line, and those that are observed, right? And the residual is the differences between the line and the actual data, which is our error in predicting, right? So the residual is the same thing as an error term. So here you can see what the method of least squares is doing. Like I kind of drew, but it was really ugly before. So this is our best fitting line, our regression line here. And obviously each point is not going to perfectly fall in the line. So the distance from each point to the prediction line is the residual, like I mentioned here. This point is basically fitting on the line, so its residual is very small. Okay, so what the software is doing, or what you would do if you ran this in a formula or just did it yourself, is you want to minimize all these distances, right? Because if you move the line up, for instance, if it was here, this point would be closer to the line, but these points would be much farther. So then these are contributing much more error terms. So what you want to do is minimize the residual as much as possible. And when you do this statistically, what happens is that you get an F statistic, and we've seen an F statistic before, right? This is drawn from our ANOVA table, and the F statistic is used to test the regression model's ability to predict an outcome, okay? And we've seen this in correlation, this R squared term, where R squared represents the amount of variation in the outcome explained by the predictors, right? And again, our R squared gives us the estimate of the size of the relationship, right? So how much of the variability in Y is explained by X, okay? So we have two things that we want to test statistically. We want to test the overall regression model, and that's followed by that we want to test the individual predictors of the beta, right? So we have predictors, right? We want to test the intercept, and we also want to test the slope. So the value of the beta in a regression equation represents the change in the outcome resulting from a 1-unit change in the predictor. And we can test this predictor statistically to determine if a single predictor is significant, right? So first we had our F table to determine if the overall model was significant, but in our beta table, we can look and see whether each individual predictor is significant. Okay, so if that beta is significant, the independent variable for that beta statistically significantly predicts the outcome. Okay, so I hope you understand the difference between the two. You have an overall model which is using F distribution to test whether the model is significant. And then with the beta table or the beta test, you can test each individual predictor using a t-test. So there's two separate concepts that really work together to let you test kind of a similar but related but also different things at the same time. Okay, so make sure you review this and understand this. Okay, so let's go over the example. So I hope you have the data available and you can try this yourself. So the simple linear regression example is the data in the record, I forget what it's called, but go ahead and look at that. So the record company's boss was interested in predicting record sales from advertising. So there's 200 observations. The outcome variable is sales, which is the number of CDs sold and downloads in the week after release. And then the predictor is the amount in thousands of dollars spent promoting the record before release, right? So 40 actually means 40,000 because it's thousands of pounds, right? So even though it's coded as 1, it really represents 10,000, right? Or 1,000, I take that back. So you're trying to see, right, does money spent promoting cause number of sales, right? So that's kind of different from correlation, where in regression, it kind of makes sense for us to put an effect direction, right? That the predictor causes some change in the outcome, right? So that's different from correlation. So make sure you know that one, we kind of want to put in the framework of saying that there's something causal, where in correlation, we don't really want to, we don't have the ability to say that, right? We just say that two things are correlated or they're associated, okay? Go ahead and look at the data in record1.save, and you see that there are 200 rows, each representing a different record, right? So one column is the money column, and the other column is the number of sales in each record. So for regression, the outcome in any predictor should be in different columns. So we kind of saw that in correlation as well, right? So that each line represents an observation, and those things are tied to each other, right? That one CD sales represents their money, and that's the same ID that represents the same person, okay? So this is pretty straightforward on how to run it. So what you would go ahead and do to run a simple linear regression, this will give us the parameters, and this will describe the regression line, and then we can also test it statistically, right? And this is pretty much the same thing we've seen before. So you'd go ahead and just click the Analyze under the regression box, and then under the linear test, we want to make sure that our sales are in our dependent box, right? Because that's our outcome of interest. And then we want to put our adverts variable into our predictor variable, or independent variable. And then you go ahead and just click OK. So you can see how we do that there. We don't need to do anything too fancy. When SPSS runs, it gives us a couple of different tables. So firstly, we get the R and R squared table. So similar to what we've seen before in correlation, right? So we get an R, and then the R squared term is just going to be the R value squared, okay? And that's saying that advertising expenditures account for 33.5% of the variation of our Y, or in this instance, the record sales, right? So our R squared is just converted to the percentage, right, drawn from our R statistic here. Okay, so that's all we need to know for this table. And like I mentioned before, remember we have both an F test that tests the overall model, and then we have a beta table that tests individual predictors. So let's take a look first at our ANOVA table, right? And this tests our overall model. So this table is pretty much drawn the same as what we've seen before, right? That we've seen in ANOVA table. So we have our regression sums of squares, we have our residual sums of squares, and then we have our total sums of squares. So this is just the distance basically partitioned into the regression line and then the total line, which is the overall error, and whether the regression line is doing better than the residual line. Okay, so let's take a look at the table, and you can pretty much reconstruct the same way that you've reconstructed the ANOVA table as before. So the degrees of freedom, let's walk through it. In our regression, this tells us that how many parameters we are testing, right? So there's one. That means we're only testing one predictor, okay? Our total degrees of freedom, so down here, this is telling us n-1 participants are in this data set, or n-1 observations are seen. So that means there were 200 lines of data in this, right? So we just do n-1, so there's 199. Our residual or error term in this ANOVA table is just going to be the n-1 minus 1. As from the top part of the table, right? So that gives us the 198. To get our mean squared regression term, we just take our sums of square of the regression term divided by our degrees of freedom of the regression term. So that's going to be the same value. Our residual mean squared term is created by the residual sums of square divided by the residual degrees of freedom. So this 862264.167 divided by 198. That gives us our mean squared of the residual. To get our F statistic, so this value here is going to be the mean squared regression term divided by the mean square of the residual term. So that's how we get the 99.587. So we've seen this before from our ANOVA table. It's drawn exactly the same. It's created the same. It's derived the same way. It's basically looking at, is our model doing better than the error term, right? So we look at it in the same way in terms of variance. Is our variance of our between terms better than the variance of the within, right? So if this is high enough, right, in terms of a statistic, that means our p-value or the significance level will be very low, right? So here it's 0.000, so very statistically significant. So we interpret that by saying that the regression model results in a significantly p less than 0.001, a better prediction of record sales than if we use the mean as a model, right? So what we're trying to do is compare the effect of whether our regression line does better than our mean. So if you think about our line, if you think about the data, so let's assume that we have, I'm trying to draw this here. So let's say we have a couple of points here, and we drew some sort of regression line, right? So what we're saying is this line, this regression line, this slope is doing much better than the mean. So what would the mean look like? Think about that for a second, right? Would it be sloped? No. What it's going to look like is just the flat line that basically is the mean value between all the y's, right? So all the y's meaning our record sales. So that's the mean, some mean point within of our record sales. So what we're saying is this regression line is explaining more than just the mean alone, if that's statistically significant. Okay, so that's how we interpret that. But this ANOVA table only tells us whether this overall model is fitting better than our mean, but we still want to look at the individual contributions of the predictor variables. So your SPSS output will also give you the effects of the parameters. Okay, so here we have two parameters because we have the constant, right, which we call the intercept, right, where x is equal to 0. Where does it cross the x-axis? And then we also have the effect or the slope of the independent variable, or here we have the advertising budget, which is in thousands of pounds. Okay, so how we interpret this is that, let's look at the intercept first. So the outcome when x is 0, when no money is spent on advertising, 134,140 records will be sold. So that's here. So when x is 0, so when you don't spend any money on advertising, we would still sell 134,000 records. And that effect is statistically significant here, right? So the effect of the intercept is statistically significant. The slope, we see that is the change in the outcome associated with the 1 unit change in the predictor. I know that's kind of confusing, but let's say that. So we said that each 1 unit is actually 1,000 unit change. So here we say for each unit change, which is 1,000 pounds or $1,000, for that we increase on spending for advertising, we would sell an additional 96 records, right? Because, and we need to multiply that by 1,000 because the independent variable is in the thousands unit as well, right? So for each increase in 1,000 pounds that we increase on spending, an additional 96 records will be sold. So make sure you understand what this beta is telling us. So for each unit change in this variable here, right, this is how much our dependent variable changes, okay? And that effect is statistically significant, okay? So we don't really need to truly interpret our intercept. What we're interested in is in the slope, right? Because that's telling us is whether our change is statistically significant, okay? So all we want to really make our conclusion on is based off our independent variable, all right? So one more other thing to note is that we can create our t statistic, so kind of like the ANOVA table, given that we know our beta and standard errors for both of these parameters. So our t statistic is just going to be the beta divided by the standard error. Okay, and I'll show that in the next slide, but I'll just write the formula. So just to go over that, it's just to get our t statistic, it's going to be our beta divided by the standard error for unstandardized coefficients. Okay, so 0.096 divided by 0.01 will give you a t-statistic of 9.97. So this divided by that gives you this. Same thing with the intercept or the constant. The 134 divided by the 7.537 gives you your t-statistic here. So then the last thing we want to look at is our standardized coefficients, or the standardized betas, which is in that third column that you see circled there. So this lets you compare across different models. So let's say you ran, we have this advertising budget and then how it affects record sales. But say we were interested in another variable. So for instance, we wanted to look at whether the size of our record sales stores affects our record sales. So the dependent variable is the same. Here, record sales, but our independent variable is different, right? So they could be different in terms of just how you count them, right? Because size is in square foot, and then this budget's in terms of thousands of dollars. So those things aren't really comparable to each other. When we standardize, this lets us make comparisons between the two. So we could say, okay, if this beta is 0.578 and the beta for in the model of size of the record store and how much they sell is one is higher or lower than the other, that lets us compare how much stronger the effect is of one variable on the other. So if this was 0.578 in the first model, but 0.9 in our model with the size of the record store on how it affects record sales, we could say that, yeah, the effect of the size of the record store is stronger than just that of the budget, because we've standardized it and allowed it to make them comparable across different models. Okay. So like anything that we do, we always have the conclusions. So here we just take our output that we have from those three tables that we've generated. So we say that simple linear regression was performed to identify predictors of record sales, or Y. This indicates that the model was significantly predicting record sales. So we have the F statistic with 1 degrees of freedom to 198 degrees of freedom. And the P was less than 0.001. And this explains 33.5% of the variation in the outcome. So the budget, right, of the beta that's shown there was significantly predictive of record sales, and we list the p-value there. The relationship was positive. Okay, so you don't have to interpret that if the relationship is not significant. So what you'll notice is that you have the ANOVA p-value telling you one thing, and you'll have your beta p-value telling you another thing. So for simple linear regression, these things should always be concordant. They should always agree, right? So if you reject the null hypothesis here, you're also going to reject it here. There won't ever be an instance where if you fail to reject it and you reject it here, and you'd have to make some weird conclusion. There's no such thing. So those things will always be pretty much the same, right? Your conclusions about whether to reject the null hypothesis will always be the same for both the ANOVA table and for your individual parameters. So the last thing we want to do is using regression equations to predict. Okay, so remember the formula of how we wrote out our y equals the intercept plus the slope. So what we would write is the intercept value, which was that 134.14, plus the beta for the advertising budget, which was 0.096. Okay, so that's times the advertising budget. So we can plug in any value that we want for advertising, right? And we can see how many record sales we would expect to make. So if we spent $100,000, how many records would we expect to sell? So all you do is plug in this 100,000 into the model here, right? But remember, 100,000 really is 100 in the context of this model. And if you multiply this term out and then add it to that 134.14, we would sell 144,000 records. So take a look and make sure you understand how to do predictions given that you know a regression equation. Okay, so I could give you any value, right? What if you spent 99.99 pounds, right? What if you spent only 1 pound, right? You know how to put any value in, given that you have this equation, and predict how many record sales you can make. Okay, so that's going to be it for this. Let me know if you have any questions. I'm available via email, and hopefully this makes sense, but make sure you practice with this and make sure you can understand these concepts, right? So with regression, not only are we interpreting multiple tables, we also want to make predictions on the regression equations that we get.